Hey, Physics 30s. Hopefully you're doing all right out there. Um, Today, if you can believe it, we are already on lesson 6 in Unit 3. If you're not already there, flip your workbook open to lesson 6 and we'll get going. We're talking today about the magnetic force on a charged particle. You see actually lots of similarities between lesson 5 and lesson 6. Just now we're talking about that magnetic force on an individual charged particle rather than acting on a wire. So let's jump in and let's check it out. This actually, I guess I should say this is from a few units ago. This is something to think about here, something that you run into every once in a while. Could we figure out the magnetic force? And I know we're going back a little bit here, but could we figure out the magnetic force between these two wires? So first off, I'd want to think about, well, if I'm talking about wires, what hand rule, and talking about magnetic fields and wires, what hand rule works really well for that? And if you're thinking to yourself, left hand rule number 1, you're doing all right. You're absolutely doing all right. And then if you think of yourself, left hand rule number 1, we know with left hand rule number 1, our thumb is the direction of the current, and our curled fingers is the direction of the magnetic field around that wire. So for the first one, it looks like the current is going into the page. So I'd have to have my thumb pointed directly into the page, and then my fingers are going to curl around in this direction. Perfect. And then the second one, so that doesn't really help me out too much there with whether they're going to attract or repel each other, because there will be a force on these two wires. The second one looks like I've got my thumb coming, or the current, and therefore my thumb coming out of the page. So I need to have my thumb pointed directly out of the page, and then my fingers are going to curl around this way, like that. So one of them, this one is curling, let's see, counterclockwise, and this one we see is curling clockwise. Cool. So now the question is, are they going to attract or repel each other? So what we have to do is we have to look at the little chunk of the magnetic field that is right in the middle. So right in the middle, the magnetic field from both of them are going to go upwards. And then we think to ourselves, so magnetic field, I'll label it. We think to ourselves, well, do like things attract each other or repel each other? Remember, opposites attract, like repel. And because we have like magnetic fields in the middle, they are going to repel, or in other words, these wires are going to have a magnetic force. I'll change the color. Magnetic force away from each other. They are going to repel. So a little bit of review from things that we've looked at, and a different way to look at things that we looked at before. Now, I promise we'll be jumping in to the new stuff. So the magnetic force on a freely moving charge, that's just a charge that's hanging out there, all on its own is moving around. So it could be an electron, could be a proton, could be just whatever charged particle we've got. And yeah, we want to check it out. So the hand rule itself, hand rule number 3, still applies. And in this case, we're dealing with an electron. So we're dealing with a negative charge. So we want to use left hand rule number 3 in particular. So our thumb is still the velocity. Our straight fingers are still the external magnetic field, and our palm is still the magnetic force. So just take a second. You can put it on pause if you want to. See if you can make your hand fit this top example that we've got up here. So you can look at the diagrams off to the side. So there's a picture of my left hand and a picture of some other cartoon's left hand. You can use that for reference, but see if you can make it fit. Put it on pause if you need to. Go. All right, so hopefully we've made that fit. And again, over here, we can kind of check out, oh, that's moving everything. That's strange. Anyways, we can check out with my hand over here, we've got my fingers pointing towards the left, because that's the direction of the magnetic field that we're looking at here. I've got the force, which is my palm, vertically upwards, and then the direction of the velocity of that electron is coming directly out of the page. Again, right angles are where it's at with this one. One quick thing that you might want to think about is, can we figure out which pole these magnets are? So maybe take a second, put it on pause, think about with that magnetic field, which pole it's on. So if you guessed that this is the north, well, actually, I hope you didn't guess, but if you figured out that that's the north and that's the south, you're doing all right. So north and south, that would create a magnetic field that in this case is going towards the left. Awesome. So things that are a little tiny bit different here is now, because there are lots of positively charged particles out there, there's protons, there's alpha particles, just to name a few, we will definitely be needing hand rule number 3 a lot more. So hand rule number 3 is for positives. Make sure we're good to go, and make sure if you're using a negative, use your left. If you're using a positive charge, use your right. But everything else is exactly the same. So you've got the physics gang symbol one up here, and then we've also got the photo of my hand down at the bottom here. Both of those are trying to match what you see on the page in the top left-hand corner. So you've got the magnetic field going into the page. So that means my fingers on my right hand need to be pointed directly into the page. We've got the velocity, and here's my fingers over here. We've got the velocity of that charged particle. Initially, it's starting out going towards the right. So the velocity is my thumb going towards the right. And then finally, we've got the magnetic force is my palm, and the palm is vertically upwards on the page. So again, hopefully, I'm going to erase that because it just makes my hand look way worse. But hopefully you can see this no matter which version of hand rule number 3 you are using. So again, long story short, left hand for negative charges, right hand for positive charges. The hand rule itself actually looks the same. The formula looks slightly different. So if you remember from the last lesson, we had Fm is equal to Lib. So that was from the last lesson. This is for wires in an external magnetic field. Now our new formula looks fairly similar, and actually if you mess around a little bit, especially if you mess around with the units, you can make our second formula out of the Fm is equal to Lib. So our new formula for a magnetic force, I'm not even going to write that out, for a magnetic force on a charged particle in an external magnetic field, we've got the charge of the particle times the speed of that particle times the perpendicular magnetic field. So again, there's that perpendicular that we're talking about last lesson. Very important that it's perpendicular. Same standard units that we were talking about before. So charges have to be in coulombs, speed as usual needs to be in meters per second, and magnetic field measured in Teslas. Perfect, so we've got Fm QVB, brand new formula to deal with. So again, very similar to this, a challenge if you want. You can try and make them look the same, focus on units, and I bet you could figure it out. Perpendicular is kind of important, and we are always looking at our maximum magnetic force. And again, if the magnetic field is parallel to the speed, then our magnetic force is 0. So same things that we talked about in the last lesson, exact same things, except again, we're looking at individual particles. Nice. So one thing to think about here is if the magnetic field, and well, therefore the magnetic force, is always perpendicular to the velocity, what type of motion is it going to get into? Right? And this is something that we looked at in Physics 20 quite a bit. There's actually a very particular physics principle that this corresponds to, so maybe have a look at the back of your data sheet and see if you can remember the physics principle. And if you're thinking it's physics principle 2, circular motion, you are, well, it's messy, you are right on track. So let's even just check out this example that we've got right here. So I've got an electron moving in an external magnetic field. So the electron is originally moving to the right. The magnetic field is into the page. Put it on pause and see if you can figure out the direction of the magnetic force for the electron as it is drawn right there. All right, so we've got out our left hand because we're dealing with negatives. Now we need to make our, so we're looking for the magnetic force. We need to make our left hand fit the magnetic field and the velocity. So let's see, the magnetic field is into the page. I chose the picture of my hand where my fingers have to be into the page. So when I rotate this, no matter what, my fingers are into the page. Perfect. I just now need to line up my velocity. So my velocity is going to be the thumb. Velocity is towards the right. So I need my thumb pointed towards the right. And then the only way that my palm can face for this one is downward. So right off the bat, the magnetic force is going to be downwards. So perfect. I'm going to see about getting rid of my hand there for a second. Just put it towards the bottom. So we see that downwards, so that electron is going to be deflected downwards. Very, very nice. But it's still got a perpendicular magnetic field. So if I look at the electron just a little bit further after it's been deflected, maybe look at it at the, at the bottom over here, I'd go through and I'd say, okay, well, I can get that hand rule out again. So here's my hand rule number 3. Now the velocity tangential to the circle. So let's draw the velocity vector in. Velocity vector. So now I just need to rotate my hand, so again it matches. So the thing that hasn't changed, the magnetic field is still into the page. I can rotate this. Now my velocity is, let's see, at about an angle like that, knowing that the velocity is my thumb. And then which way is the magnetic field, or sorry, the magnetic force? Well, it's still my palm, and it's still towards the center of the circle. So you've seen stuff like this before, this whole idea of circular motion, where the magnetic force, in this case, is perpendicular. Magnetic force is perpendicular and always perpendicular to the velocity and always perpendicular to the magnetic field, and it creates nice circular motion. So if we go back to our physics 20 thoughts and we want to figure this out, physics 20 we said that F net, realistically, it is Fc. So centripetal force is like a fancy word for net force when it's in circle. It's the sum of all the forces. So I can expand on this and I can say Fc. Well, if it's the sum of all the forces in this particular case, the only force we really have acting on that electron is, oh boy, okay, things are getting worse here, it's bouncing. The only force that I have acting on that is Fm, so then I can go through and I can start to expand. Well, Fc, that's just my net force, that's m times a, but a very particular acceleration, it's our centripetal acceleration, so I put ac, and then Fm, well, Fm, we just learned a formula for that, right? It's q v b. Very, very good, very nice. I'm gonna, again, try and get rid of my hand. Maybe I'll put it over on this side for now. And then, yeah, but the thing is, like, we could probably expand on this a little bit more, because remember from physics 20, we have 2 formulas for AC. The formula that we're going to use the most is v squared divided by r. The one with period in it, so that's 4, I'll write it out for you, 4 pi squared r over t squared. You don't really use that one nearly as much. I'll put it in brackets, but this one, this formula for AC we do. So we can expand on this one more time. We can say m v squared over r is equal to q v b. And now we've got a formula that we can work with. You're probably already starting to recognize that v squared is just v times v. It cancels one of those ones. We'll write it out one last time. mv over r is equal to q times b. And then we can rearrange this and we can look for all kinds of different things depending on the question here. So again, circular motion is kind of key. And when we review circular motion, F net is the same thing as Fc. It's the sum of all forces. It's mass times acceleration, just for circles. So in this case, Fc is equal to Fm, and we can expand on that and we can build a formula. So this is something that you'll be expected to do through the course, is build that formula. So let's see it in action here. We've got this example. It's a bit of a doozy for an example. It's a lot going on here. A little bit of Unit 2 stuff, a little bit of the electricity stuff, and then the new circular motion pieces. So let's go through, we'll make a game plan, and then I'll get you to get a head start on it. Pause the video and get a head start. So we've got a proton. We know lots of stuff about a proton. It's accelerated from rest, that seems important, through a potential difference of 40 kilovolts. So that's what's going on in this top part right here. From rest, across a potential difference, those parallel plates of 40 kilovolts. Let's see, it then enters a 580 millitesla magnetic field that is out of the page. Okay, so here down at the bottom, that is my magnetic field, and that's this grayed out area at the bottom, so it's going to enter that, and then it's probably going to go into circular motion, right? That's what we were just talking about. So the first part of the question is determine the radius of curvature in the field, and they're talking about the magnetic field for that one, because it's not going to curve in the electric field that's there, but the magnetic field definitely. And then the second part is it clockwise or counterclockwise? So let's just think about a plan here, and I wouldn't start writing anything out yet. We know that it's going to be circular motion in the magnetic field, and that's sort of our goal, is to figure out what's going on in that magnetic field. So I know that Fc is equal to Fm. When you start to expand on this, even right here, and mv squared over r, oh no, we're missing v. So we should, oh, no arrow on top, it's a speed, not a velocity, silly me. So we should probably try and figure out speed, right? And I bet you we can figure out speed from the top part, from the parallel plates up here. Perfect, so we gotta remember with those parallel plates a little bit, we gotta remember how exactly we can figure out and deal with protons and other things accelerating across parallel plates. Does anybody remember the two physics principles that we could use? If you're thinking to yourself, physics principle 1, accelerated motion, good stuff, absolutely. Or physics principle 5, or conservation of energy, good stuff. You could probably use either of those. Actually, you might not be able to use physics principle 1 for this one. And remember, physics principle 5 is typically the way to go. So physics principle 1 is really good for if you have the distance across the plates, definitely, or if you're looking for the time it takes to get the proton to go across the plates. Physics principle 5 is typically our go-to for everything else. It's a little bit easier to deal with. So we've got a game plan for this now. We're going to use physics principle 5 to figure out the speed as the proton exits the parallel plates, and then we're going to use that speed and circular motion, that's physics principle 2, to figure out the radius of curvature while it's in the magnetic field. So at this point, put your video on pause, try it out. We've got a plan, try it out. All right, so let's see where we're at here. I am using ETI is equal to ETF. So I said we're going to start with a lot of potential energy. All of that potential energy is essentially going to change into kinetic energy. So we're actually using delta V is equal to the change in electric, or change in energy, divided by Q. So we rearrange and we say, okay, well, all of that energy is starting as potential and turning into kinetic. So I can go through, maybe I'll use a different color as a bit of a highlighter here. Use yellow, hopefully people can see that. We went through and we said delta V times Q, that's my potential energy, that's all of the potential energy that I'd have at the one side, is equal to 1/2 mv squared. So potential is turning into kinetic. We can go through and we rearrange, solve for the speed. So keep in mind that there's two V's in this equation. One's a lowercase, the other's delta V and capital. As I rearrange and I solve for my speed, I would have to make sure when I plug in numbers that I'm using my standard units. So that's 40,000 volts instead of 40 kilovolts. We are using a single proton, so it's going to be just 1 times our elementary charge, 1.6 times 10 to the negative 19. We're going to divide that by 0.5 and divide that by our mass of A. I forgot a close bracket there. Proton 1.67 times 10 to the negative 27, remembering that that information comes from our data table. And it turns out the speed is 2.6785 ... times 10 to the power of 6 meters per second. So remember from last unit, we're talking about how individual protons and particles can go ridiculously fast, but not too fast. This fits right into that category. It's not over our speed limit of 3 times 10 to the power of 8, but it is still ridiculously fast. Now there is one other way that we could potentially look at this. Let's get back to, I don't know what color I had before. I'm going to choose that one. We could also go through and look at this in terms of delta V is equal to our change in energy divided by Q. So as I go through and as I look at this, I'd say, oh, well, my change in energy is equal to delta V times Q. It's the kinetic energy that's that's really changing in this case. So I could say my change in kinetic is equal to delta V times Q, and I know that it is gaining kinetic energy, so I'd call that positive, and then I'd end up with, okay, so change in anything is final minus initial, so EKF minus EKI is equal to positive delta V times Q. Well, there is no kinetic energy, so we end up with realistically the same formula. EKF is equal to delta V times Q. So different way to see the same thing and to get to the exact same place. Perfect. Either way, we figured out the exit speed as it leaves the parallel plates. Now, I would argue probably the easier part for this is to go through and figure out the radius of curvature. So for this one, we are using, let's go back to a bit of a highlighter color. We are using physics principle 2, and we know that physics principle 2 is Fc, which is the same thing as net force, is a sum of all the forces, in this case, Fm. So we expand on that. Fc is m times AC, Fm is Q VB, but hey, I don't really want AC in there, so I'm going to replace AC with V squared divided by R. Awesome. At this point, I'll try and get back to my original color. I think I had like might have been that one. So I'd go through and I'd start to rearrange this, solving for the radius of curvature. Okay, so let's first get rid of one of these speeds. So now I've got mv over r is equal to q times b. Excellent. Excellent, excellent. I'm solving for r, so r must be equal to mv over q b if we rearrange correctly, and then we just need to plug in a few numbers and solve. Okay, cool. So I got the numbers plugged in, remembering standard units, remembering masses and charges come right off our data table. And it turns out that I forgot to write the actual answer down. What color was I using? I think it was that one. So when I plug all the information in, we end up with, let's see, 4.98 centimeters. Actually, it would have turned out in my calculator 0.0498 meters, but we changed that to centimeters. Just, I don't know why. You don't really need to for this one, I suppose. But one thing to keep in mind, this seems pretty insignificant, right? 5 centimeters. A lot of these devices that people see and that we use with this are actually about that size. So like fit in the palm of your hand kind of thing, or a little bit bigger than palm of your hand. Cool. So a little bit of review from last unit, and then the new stuff with Fm is equal to QVB, and the idea that it's moving in circular motion. Our charges are going to be moving in circular motion. Cool. Last part of this one, very, very last part of this one is, well, can we determine which direction it's going to be deflected? Is it going to be going clockwise or counterclockwise? So we know it's a proton in an external magnetic field. We know we're going to be using right-hand rule number 3. So take a second, see if you can figure out the direction of the magnetic force, and then that direction of the magnetic force is what's going to tell us the whether it's clockwise or counterclockwise when it gets into circular motion. So go ahead, put it on pause, and try and figure that out right now. Alrighty, so I had to go take a new picture of my right hand. I'm turning into quite the hand model here. So looking at this one, the thing that I've got lined up is I've got my fingers pointing out of the page. My fingers have to be pointing out of the page in this particular picture. The only other thing I really need to do is now line up my thumb, which is the velocity, and the velocity is pointing down, and then we can clearly see that the only direction my palm can face, which is my magnetic force, has to be towards the left. So initially, I'd better choose a different color here. Gray on gray isn't going to work so well. So initially, the magnetic force, Fm, is towards the left, which is going to cause this proton to swirl around. And it's going to swirl around, if we compare that to a clock, that is the same direction that a clock goes. So we're going to call that clockwise, CW for clockwise. Excellent. So yeah, that's the scoop there. Again, this is sort of the end of the main part of the lesson. So if you want to stop the video and start working on some practice right now, that's okay. That being said, there is another little piece that we could potentially look at here. And it's actually a pretty cool piece as well. It's understanding how skip that one, understanding how northern lights work. So you might even recognize this picture. This is taken over Edmonton. And some of my favorite pieces, again, I'll mention this part, you don't necessarily need to stay on the video for, but if you're interested, by all means, stick around. So yeah, northern lights are just one of my favorite things. When you see them, it's just so cool and such a spectacular sight. And honestly, every time I go outside in the evening, I look up and see if there's anything there. Unfortunately, living in the city with lots of light pollution, we don't see them as often as, say, you were out in a rural area, but that's okay. It makes them extra special when we do. Things that you can note, University of Alberta actually has an Aurora watch that will send you alerts when there's a high likelihood of seeing northern lights or aurora borealis. You can sign up for this and they'll send you emails when there are high chances or high probabilities of seeing it. So let's just check out how this works real quick. So things that we know. We know that the sun gives off a solar wind. The solar wind is tons of high-speed particles, electrons and protons and different pieces there. So electrons, protons are coming out at high speeds away from the sun. Perfect. We also know that the Earth has a magnetic field. Now, if you remember the Earth's magnetic field, make sure I can draw on things here. If you remember Earth's magnetic field, our geographical north is our magnetic south, and our geographical south is our magnetic north. And if we wanted to trace the field lines, we know that the field lines go away from north and towards south, because it's the direction that a compass needle would point or the direction that a North Pole would want to go. Awesome, so we've got that one there. Here's a little bit nicer of a picture of that, but similar kind of idea. Now, if we have this solar wind traveling in an external magnetic field, we know through hand rule number 3 that it's going to curve and it's going to go into circular motion. Now, that being said, this isn't going to be perfectly circular motion because it is not a perfectly uniform magnetic field, but it's going to go into circular motion like patterns. It's actually going to go into spirals typically as they lose energy with our field. So knowing this actually gives us this 2 pretty cool effects, this solar wind coming and interacting with our magnetic field. It gives us protection. Without this, we either would not be here at all. Without our magnetic field, we would not be here at all, or things would be very, 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 very different, because that solar wind is actually ionizing radiation, which can destroy our cells and destroy our DNA. So that's no good. So it offers protection. And then the other thing is it offers the northern and typically southern lights. So how both of those things work? Well, we kind of already went over the protection piece here. So the particles don't actually make it to the surface of the Earth. They spiral, they lose energy, they're deflected. So all that ionizing radiation doesn't make it here, so it can't destroy our cells, which is perfect. That's exactly what we want. The other piece of this is the northern lights. So when these charged particles hit gases in our atmosphere, they actually cause them to jump up and get into a higher energy state. So they cause them to vibrate a little bit quicker, cause them to come up to a higher energy state, but they don't really like being in that higher energy level. So if I've got my particle, I don't know, I'm just going to draw that as my particle. It's got different energy levels. It might bump it up to a higher energy level, so vibrating a lot quicker, things like that, but it doesn't like to be up here. So as it falls back down, it actually gives off that extra energy in the form of a photon or in the form of light, and that's what we see as our northern lights, right? It's that solar wind interacting with our atmosphere, giving it extra energy, and as that energy drops back down, it gives it off as light, which is very, very cool. There are different gases that give off different colors. So you can see the couple different colors here. Interesting things to note from this is the different colors actually come from different gases. So oxygen, not a felt pen, oxygen that's typically very high up in the atmosphere often gives red. When you get oxygen at lower levels, it oftentimes gives green. Nitrogen is known for red and blue. And then, of course, there are some blue, kind of ran out of space there. There are some other colors, and of course there's mixtures of colors. So pretty cool stuff, actually, these northern lights. I definitely recommend that Aurora watch. It's pretty cool. Oftentimes the things come in at like midnight or 2 a.m., so you miss them anyways. But when you catch them, it's cool. And keep your eyes on the skies because you see a lot of cool stuff up there sometimes. Anyways, that is now really it for today's lesson. Good stuff, Physics 30s. Keep working hard. You've got this, and we'll see you again soon. Bye for now.